So let's see the assumptions that Einstein made. He started by assuming that Galileo's principle of relativity was true, that physics is the same for all inertial frames. He dealt with the tricky problem about the ether by saying, well, let's forget about it. Maybe light doesn't actually need any medium to oscillate in. Most importantly, he assumed that the velocity of light is the same for all observers. Now that is required by Maxwell's equations, and it's been demonstrated by the Michelson-Morley experiment. So we have an important thing that Einstein puts on the board in the absolute column, the speed of light, seen as an absolute quantity that everyone agrees with. So basically Einstein sided with Maxwell and said that Newton must be wrong. So we'll have to take Newton off the board now and replace him with Einstein. We're developing a new set of rules according to Einstein. So, in order to look at the way that Einstein developed this in his paper, I'm going to use a slightly different approach to the one he used, but one that I think is a little bit more interesting, using Einstein's train. So, we need 2 more volunteers for this. So, we've got another 2 people who are prepared to volunteer. Joe, will you 2 come down here? This side, we'll give you some hats. Why don't you take the blue hat and on the red hat? And we've got some cards there which we'll explain what to do with in a moment. Now, one of you, the red observer with the red cap, is going to associate yourself with this observer here, this little man on the platform. And you're the blue observer, so you are this man on the train here with the blue hat. And the idea is that you want to find out whether Einstein's train here is longer than the platform or shorter than the platform. And to do that, we've rigged up some lights at the front and back of the platform and some switches on the train, so as the train comes past, the light goes on at the front and then on at the back, okay? Now, if the train is longer than the platform, it's going this way at the moment, if the train is longer than the platform, the light at the front comes on before the light at the back, okay? If the train is shorter than the platform, I'll just remove a couple of carriages to make it shorter. So if the train is shorter than the platform, look what happens, the back light comes on before the front one, okay? And naturally, if the train is the same length as the platform, then both lights come on at the same time, okay? So we've given you cards to say when the light comes on. You've got front and back cards that you'll hold up for everyone to see when you see the relevant light comes on. The only thing is that this is Einstein's train, which is travelling very fast, very close to the speed of light. So we have to make allowance for the finite time that it takes light to move. And the best way for doing that is for the red man on the platform to position himself midway between the 2 lights, so that the time taken for light to reach him from either light from either end is the same. We don't ever need to worry about that. Likewise, the man on the platform on the train positions himself midway between the 2 switches. So again, you don't need to worry about the delay. So let's see what happens as the train comes along. Here it comes along, the lights come on now, but don't put up your cards yet because you haven't received the light yet. The lights come on, but you haven't seen it. As the train goes along, let's see what happens. These are the light photons setting off from the little lights, and neither of you have seen the light yet, but what happens now, the blue observer sees the light from the front. So put up your front side, you see the front light. A little bit later, what happens now, the red observer sees both, you put both of those up, and I don't think you'll quite reach it, but if it did, well, no, the red observer would eventually, sorry, the blue observer, the blue observer would eventually reach this light, you would eventually put up your back one. So let's see what you think about the length of the train. Which did you see first, the front or the back? And does that mean that the train is longer or shorter? Can you remember? That means the train is longer. So you think the train is longer. Which did you see first? Both at the same time. So you think it's the same length as the platform. So they disagree about the length of the train due to just this simple little reasoning. That's a rather surprising result, but that's what Einstein was saying happens in relativity. Okay, give them a big round of applause. Just in case you were all confused by that, we've got a little animation to take you through it again. This is the moving observer in blue on the train and the red observer stationary on the platform. So the train comes along and the light sets off from both ends of the train, as indicated by the little yellow dots. and the light pulses start moving towards the observer, and now the blue observer sees the pulse from the front of the train. The observer hasn't seen anything yet, but now he sees both of them together, and then eventually the blue observer sees the one from the back of the train. So by that logic, the moving observer in blue thinks the train is longer than the platform, but the stationary observer in red sees that the train is the same length as the platform. They disagree about length. So length is not an absolute quantity at all, it's relative according to Einstein. It depends on the observer if the observer is moving. So we have to move it to the relative side of the board. Now, the reason they disagreed about that sort of thing is because they didn't agree about whether or not two events occurred simultaneously, whether the two flashes of light occurred at the same time. That loss of simultaneity obviously affects our perception of time, so we need to think about what happens to moving clocks. So we've got another little Gedanken experiment to think about moving clocks. So 2 more volunteers, please. Anyone else prepared to? So yeah, 2 people at the back there. Group 2. You get a red and a blue hat each. And you each get one of these little devices which I call a nanosecond metronome. So if you just come and you take one of those each. One of you stand there and one of you stand here. Okay, let's start with the blue one here. Let me just demonstrate how this works first of all. This has got 2 mirrors opposite each other, and Heather will just set it going by putting a little flash of light in there between them. So the light flashes there, down, and back and forth between the 2 mirrors. There you see, there's a little light photon going back and forth. Now, I call this the nanosecond metronome, because at real speed, these are 30 centimeters apart, so it would actually take 1 nanosecond for light to move between them. So it's giving lots of regular ticks every nanosecond, and we illustrate that with this thing here. It is only a thought experiment after all. So that's how the nanosecond metronome works. There's yours. We're both going to have the metronomes working, but let's just check they're the same length first. So bring them side by side and see, are they both the same length? Yeah, okay, they're the same length. And the light is going to travel at the same speed for both of you. And Einstein said that the speed of light is absolute, so you must both have the same speed of light. So Heather's going to set both of your metronomes going. Okay, now they should be going in sync, so can you keep them both going together? Now, blue, can you walk across the room slowly as we're doing that? Carry on walking across the room. And we'll ask the audience, which of these light photons has to go the furthest between the mirrors, the red or the blue? Okay, you can stop now. Which move furthest between the mirrors, the red or the blue? The blue. Why did the blue move further? It's got to go that zigzag diagonal path, and it's got further to go. It goes at the same speed, but it's got further to go. You can stop now, though. Further to go, at the same speed, must take longer. So the blue metronome that was moving is ticking slower. Its tick is longer than the stationary one. So this is another surprising result of relativity. They don't even agree about time. Okay, give them a round of applause and we'll... Okay, we'll just go through a graphic of that in case you got confused by that one as well. Here is the diagram of the stationary nanosecond metronome on the left. And the light goes from the bottom mirror up to the top and back down again. And if the distance between the 2 mirrors is d, the speed of light is c, then if the time for 1 tick of this stationary metronome is ts, it must be ts is d, the distance divided by the velocity c, from which we can deduce that d is ts times c. Now the moving one went like this, up from the bottom mirror to the top and back down again. And if the mirror is moving with velocity v from left to right, then if the time of its tick is tm for the moving mirror, then the distance the mirror travels in a time tm is tm times v. Meanwhile, the light travels a distance tm times c, at the speed of light. So we can apply Pythagoras to this right angle triangle here, and we have tmc squared, the hypotenuse squared, is equal to d squared, this vertical distance between the mirrors, plus tmv squared, the other side squared. If we square those up, we get tm squared times c squared is equal to d squared, but you can get from this equation to be ts squared times c squared there, and this is tm squared times v squared. If we divide through by c squared, we get tm squared is ts squared plus Tm squared times V squared over C squared. And a little bit of rearranging of that shows that Tm is Ts divided by the square root of 1 minus V squared over C squared. That is a result that only relies on Pythagoras, but that's a rather surprising result, which is called an effect called time dilation. Just written it again here. We usually define the quantity gamma to be 1 over the square root of 1 minus V squared over C squared. That will crop up in several slides. We're going to use gamma several times. And if we rewrite it like that, we've got Tn, the time for one tick of the moving mirror, is equal to Ts, the time for one tick of the stationary mirror, multiplied by this number gamma. Now, with this definition of gamma, it's not difficult to see. As long as V is less than C, the gamma must be greater than 1. That means Tm is more than Ts. So each tick of the moving metronome is longer than a tick of the stationary one, which means that the moving metronome runs slow. Now you say, well, that's probably a quirk of this rather odd clock. I've never seen a clock like that. Real clocks don't behave like that. But no, they must do, because the principle of relativity says that you can't detect your movement of uniform motion in a straight line. So suppose there was another clock that didn't change like this. Then just like in our relativity laboratory, we would have the two clocks side by side, and if the nanosecond metronome does change and the other clock doesn't, we would know that we were moving. But the principle of relativity says we can't know that we're moving, so both clocks, all clocks, in fact, must change in the same way. So the time interval is not absolute, it is a relative quantity, just like length was. So we're finding that is why it's called relativity. More things are relative. In fact, now we're in a position to work out how long the train was. We know that the two observers disagreed about the length of the train. Let's see how much they disagreed. To do that, all we need to do is give the red observer a little can of spray aerosol paint and get him to spray a dab of paint every nanosecond on the train as it goes past, as its clock ticks. So here he goes, splash, 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 he'll spray the paint on the train. The train's going past to the right with velocity v, and it ends up with n marks on the train. They must both agree on that, they've only got to count that, that's not difficult. So the red observer said, okay, the time between my marks was t, so the distance between each mark is vt, and there are n marks, so the length of the train is nvt. That's the length of the moving train that he observes shooting past him. But the blue observer said, hey, to me, his metronome was going slow, because as far as he was concerned, the platform is shooting off in that direction, and so to the blue observer, the red metronome is going slow by this factor gamma. So he says the time between the marks is gamma times t, so the distance between each mark is v gamma t, and with n marks, the length of the train must be nv gamma t. I called that ls the length of the stationary train, because as far as the blue observer is concerned, the train is stationary. He's the one that's sitting on the train. And if we compare those two results, we get ln is ls over gamma. The length of the moving train is shortened by this factor gamma. That is just the factor that was calculated by Lorentz to explain the Michelson-Morley experiment, but now we have Einstein giving a reason as to why it should happen. So if we look from the platform, the man on the platform would see the length of the train reduced. If it's going fast enough, maybe it's reduced by a factor 2, it's half as long. But the height of the train and the width of the train haven't changed at all. So it looks squashed, and the man on the train looks rather tall and thin, and he's squashed like that. But the man on the train says, oh no, I'm okay, it's the man on the platform that's shooting off fast in the other direction. So he thinks the platform is short and reduced, and it's the man on the platform who is tall and thin. You may say, well, hang on, it doesn't happen like that. I've often watched trains going past the station, and they don't get short like that. But maybe let's work out how big this effect is going to be. This is a graph showing how big gamma is. Gamma 1 over root 1 minus v squared over c squared is the quantity that governs how big this effect is. And this is a graph of gamma as a function of v over c, the velocity as a percentage of the speed of light, c. So 100% here is the speed of light. And as you approach the speed of light, gamma becomes very large. To get a shortening by a factor of 2, which is that picture that I showed you just now, if we look across here for gamma of 2, that dashed line tells us we want to be nearly 90% of the speed of light. So we'd only get that amount of shortening on a really very fast train. That's why we don't normally see it. Normally we're right down this end here, very small velocities, where gamma is very, very close to 1. In fact, if we zoom in at the bottom left of that graph, for 500,000 miles an hour, which is the fastest we managed to go in our relativity laboratory, we read off the graph there, we see that gamma is 1.603. In other words, it differs from 1 by only 0.3 parts in a million. So it's an effect that is too small to be seen by ordinary experiments at speeds that we normally encounter.